Hello students, welcome to supplementary video lectures. Today's topic is analysis of continuous beam using moment distribution method. So based on the multiple feedback and suggestions received from you, we have started the video sessions for the topic of the structure analysis 2 subject. The purpose of these video lectures is enhancing your learning beyond the classroom lecture sessions. So, by watching these videos, you can recalculate the examples and whatever doubt you have, so you can solve it at any time as per your convenience. So, today we are going to discuss about the moment distribution method and the practice example of it. So, let's start with some basic introduction of moment distribution method. So, as we aware, moment distribution method, that is a one of the best suitable method, fundamental method. There is a iterative method, and there is a use for the analysis of continuous beam and rigid frames, and also it is applicable for multiple spans of the bridges. On site, when we have to do the some cross checking or some quick calculations or quick checks during the larger project, that also possible using the moment distribution method. Number of applications are there. Along with that, you can use the smart application using the programming in moment distribution method. So let's start with a practice example of it. So this example, in another video session, you can see that we have solved with the slope deflection method also. So here you have to compare both the method, and you can check that which method is a more suitable as per your perspective. So here we have to analyze this beam using moment distribution method. There are two span continuous beam. First span having the point load at the 3 meter distance from the A, and second span having the 30 kilonewton per meter UDL over the entire span. In the AB, there is a moment of inertia is a 2I, while the BC, the moment of inertia is a I, which is showing the changing of the cross section throughout the span. Next, we will start with the calculation. The step number one, that is a friction moment. All of us are aware about the importance of the friction moment. You have well remembered these equations. So let's apply the first friction moment to the span AB. So as it is a eccentric point load, so equation is minus WAB square by L square. Why it is a minus? Because generally whenever if you consider any particular span of the continuous beam or fixed beam, so which is subjected to the point load or UDL. So left hand side moment is anti-clockwise, right side clockwise. So as per our sign convention, what we are considering that clockwise moment is a plus and anti-clockwise minus. So here the answer will be minus 24 kilonewton meter, while MBA, that is a right side moment, that is a 36 kilonewton meter. Similarly, if we are applying the equations of the friction moment to the span BC as it is a UDL, so moment will be minus 62.5, while MFCB there is a 62.5. So this first step is a very basic fundamental, and it will be show the importance of the friction moment equation which you have remembered. Now, before moving to the next step, that is a distribution factor, we have to just discuss about the brief about the what is the meaning of the distribution factor and why it is required to calculate in the moment distribution method. So let me take an example, a simple example that suppose if it is a 100 kg weight need to be lifted by the three different men who will lift the maximum and minimum weight. So if three equal persons are there, then all should be taking the equal weight. But generally, it is not possible that all the person having the different configuration. So for example, if we have a 100 kg weight and we have a three different configuration persons, either it is a strong person, moderate, or weak. So based on their capacity, based on their stiffness, the weight will be lifted by them differently. So as strong person having the more stiffness, it will be carry the more amount of the force, and weak men having the less configuration, less capacity to lift that force. So it will be less amount of the load will be going to lifting. So what is the context behind this example? The same thing will be happen when we have to distribute any load or moment at the joint, and there are number of members are connecting to it, so that load or moment is not going to distribute equally. Otherwise, what happened that whatever weak members are there, it will be going to fail if it is a going to distribute equally. So that's why the load or moment will be distributed according to the stiffness of the member, and that stiffness is we have to calculate, right? There is a stiffness is a nothing but there is a load by displacement of that member, and according to the stiffness or distribution factor, we have to distribute the load or moment to the particular members. Now simply we will take the example of these two beam. One, there is a far end is a fixed or continuous, and second, there is a far end is a hinge or pin. So what is the difference in these two? So there is a two thing. One is a stiffness, and second is a carryover moment. So whenever it's a stiffness, so far end is a fixed or continuous, the stiffness is a more, so it will be taking the more amount of the stiffness 4EI by L. But when far end is a hinge or simply support or pin, then it is a stiffness is a 3EI by L. Similarly, carryover moment. What is the carryover moment? That whenever it's a far end is a hinge or roller, so it is a far end, that is a nothing but carryover moment is a zero, because as it is a going to rotate, so there is no moment over there. But when far end is a fix, so it will be carry the moment of the 1 by 2. Why? Because it will be distribute the half moment to the far end. We can take a simple example that suppose if it is a fixed beam, try to rotate right any one of the ends. So what we have seen that what is the moment at near end 4EI by L, and far end it is a 2EI by L. So if we take a ratio of that 2 ei theta by L divided by 4 ei theta by L, so it will be get the 1 by 2. That means whatever moment we are getting at the one end, so at the far end, half moment will be going to distribute. That is called as a carryover moment. Now, based on this example, we have to apply the stiffness and the distribution factor, and that's why we have to calculate first the distribution factor. So here, the distribution factor is like this: member A, that is a connecting to the member AB. Suppose joint C, there is a connecting to the member CB, and member BA and BC are connecting to the joint B. So here there is a one thing is mentioned that support A having the distribution factor 0, while support C having the distribution factor 1. So why it is like this? Because whenever it's a fixed support, that will be absorb and retain all the applied moment in preventing them from the being distributed to other moments. Or in general, if we take an example of the nature of the support, what is the meaning of the fixed support? That as it is a rigid, it cannot rotate or displace, and meaning is that it will be resist any applied moment internally. In another context, if we see when moment is applied or carry over to the fixed support, the support absorbs the entire moment, and because of that there is no distribution, because that support will take the full moment and don't release it. While when we are considering simply support, so distribution factor is a 1. So what is the context of it? That if simply support allow the rotation but restrict the vertical displacement, and when moment is applied to the simple support, the support is designed to rotate and release that moment, and that's why we have to consider distribution factor as a 1. So whenever it's a end support is a hinge or roller, so distribution factor is a 1, while whenever it's a fixed support, so distribution factor is a 0. Now if we talk about the intermediate support, support B, so there are two members BA and BC. If we are considering the BA, far end is a fixed, so what is the stiffness? It is a 4EI by L. So 4E I in place of that we have to consider 2I divided by 5, so it is a 1.6 EI. While BC, that is a as far end is a hinge or roller, so it is a 3 EI by L, it's a 0.6 EI. What is the summation of this two stiffness? There is a 2.2 EI. Distribution factor is nothing but the individual stiffness divided by summation of the stiffness K divided by sigma K. So it is a 1.6 divided by 2.2. So it will be 0.73. While for the BC, that is a 0.6 by 2.2, that's a 0.27. Now we have to use this distribution factor, apply this distribution factor in the tabular form in this manner. So there is a moment distribution table, member AB, BA, BC, and CB. What is the distribution factor of the AB, which we have seen in the previous table? There is a 0 in the BA, 0.73, BC, 0.27, and CB, that's a 1. So there is a first line, we have to mention the distribution factor. Next, friction moment, there is a minus 24. 36 minus 62.5 and 62.5. So which we have find out in a step number 1, fixed moments. Now there is a whenever this is the iterative method, so we have to do the balancing of the joint. So whenever we have a end support is a hinge or roller or simple support or overhang, so first we have to balance that joint. So here, as our joint CB, right, remember CB, that is a hinge, so we have to balance this joint first. So the joint, what we have to do, that 62.5 moment we are getting the CB, that is going to multiply with the distribution factor 1. So what we are getting 62.5, that we have to write in the opposite sign. If you are getting here plus, so we have to write in the minus. So here if we write minus 62.5, so that is called as a balancing of that joint. So, and as we have seen in the previous step, there is a carryover. So when, if we consider the balancing of the CB, so far end is a BC, right? While that joint B is an intermediate support. So half moment will be going to carry over on the joint B. So that is a become a minus 31.25. So 1 by 2 carryover will be there. So minus 62.5 by 2, that is a minus 31.25. Now we have to do the summation of this two row because we are balancing one end support. So that is also called as a end correction. So if we do the summation, minus 24 is as it is, 36 as it is. We have to do the summation of this minus 62.5 minus 31.25. So it is a minus 93.75. Then 62.5 minus 62.5, that's a 0. So you can see here that summation at the end will be 0 only because end support is a hinge. So moment will be 0 at the end. Now this is our initial moment. We, when we are see the final calculation, we don't have to see the upper one because we are doing the summation over here by balancing or doing the end correction of the joint C. Now we have to do the balancing of the joint B. So what is a balancing? That whatever moments, total moment at the B. So we have to do the summation. Algebraic summation is a 36 minus 93.75. So it will be minus 57.75. So that summation is a minus. So we have to write the whatever value we are getting, that is a plus. So 36 minus 93.75, that is a minus 57.75. That is going to multiply with the distribution factor 0.73. So that will be nothing but 42.16. As the summation total will be minus, here right we have to write the opposite sign. So it is a 42.16. Same way 57.75 is going to multiply with a 0.27, that we have to write at the column of the BC, that is a 15.59. Now this balancing is done. Now again we have to do the distribution or carryover of that moment. So how to do the carryover? This BA moment will be going to carry over on the joint A, that is a become a 21.08. While here BC, the far end is a hinge, so we don't have to do the carryover because it is a carryover moment is a 0. So here we don't have anything on the joint B, so there is no another iterative cycle will be required. So here it is just we have to do the summation of these two value. The first one 21.08 minus 24 minus 2.92, 36 plus 42.16, 78.16 minus 78.16 and 0. So this is our final moment. You can compare the answer with a video from the slope deflection method also. And you can see here that we were both the moment B and BC, there are equal and opposite sign. And CB, that will be 0. So there is a cross checking of the answer. Same way in the slope deflection method, if you have seen, so we are applying the equilibrium condition MBA plus MBC equal to 0 and MCB equal to 0. So in the both the method answer will be same. So you may cross check the answer with the slope deflection method also. Now let's come to the diagram part. So according to the sign of the value, we are putting the moment first minus 2.92. So it is anti-clockwise, 78.16 clockwise, minus 78.16 anti-clockwise, and last is a 0. So as all the moment are hogging only, so we have to put all as a minus and we have to connect the lines. So this is a bending moment diagram due to the support moment. Similarly, we have to put for the span moment. So as it is a point load, so span moment will be WAB by L, and that is a become a 60. And For the UDL, WL square by 8, so it will be 93.75. So what we can see over here that the span moment is a plus while the support moment is a minus. So that's the end of this example. Now let me end this video with the review question. If in place of this end support is a hinge, if additional there is an overhang span, so what will be the effect in the calculation in the moment distribution method? So you should think about it. It can be any type of the load, but what we have to think just that what is the effect of the overhang span? You can see over here beyond the sea there is some overhang portion. So what is that overhang portion effect in the calculation, and where we have to consider that you have to think about it. So give your answer in the comment section. So with this we are ending this video. If you have any doubt, if you have any suggestion, please share your thoughts in the comment section. Thank you so much, and we will meet in another video session regarding the another topic. Thank you so much.